And I'll speak about research that we did together with Professor Samko, just very recent research. We just finished a few months ago, just only submitted, it's not published yet. But I have talked to Professor Samko. He agreed that we will present this research nevertheless. So actually the title is Aggrandization of Spaces of Holomorphic Functions Reduces to Aggradization on Boundary. But I will not only speak about holomorphic functions. I will speak first about a general situation, and then I'll apply our method to the case of holomorphic functions. So my talk will be split into two parts. First part will be devoted to a general scheme of aggrandization that we invented with Professor Samko, and second part will be application of this general scheme to the case of holomorphic functions. But as I said, we consider this part the most important. Okay, well, here it's written what I said as a short abstract, but we go further, move further. What is aggrandization, or what is grand space? Roughly speaking, grand space is something that's bigger LP. It's given by this norm. You see, you take LP minus epsilon norm, so you take a norm in a bigger space, multiply by this factor, and take a supremum. Then the most important features here are P minus epsilon, and in which space you take a norm, and this epsilon to the power theta. You multiply by this factor to calculate supremum. This is not of importance at all. This is just to have a property of norms, just for technicalities. This P minus 1 not important at all. You can take arbitrary small number. You can take supremum between 0 and arbitrary epsilon 0. So no importance. Okay. Well, as you can see, the norm is pretty bad. Because when you have a supremum, well, it's not so easy to think about approximations, etc., some other issues. People also calculated norm of round space in terms of rearrangements, but even these norms are not so explicit. This is just for information. Well, once you have round space, you always have small space. I will not speak about small space, but small space is dual space to grand space. Associate, not dual. Associate space to a grand space, not dual. Dual is different. Okay, but I will not speak about small space. Small space is smaller than LP. Big space, grand space is bigger than LP. Okay, I will speak about only aggrandization. Well, these are basic properties, as I already said. Grand space is bigger than LP, but smaller than every P minus epsilon, LP minus epsilon. Also for small space. Well, Zygmunt or Marcinkiewicz space or weak LP space between, you can ask how close grand space to the space LP. So still this space is between both of the spaces. Lorentz space, also here you can see the diagram. So you can have an idea that, well, still between grand space and LP there are some other spaces. So there is difference. There is a difference. There is distance in certain sense. But the distance is infinitesimal because, you know, this supremum, you just take supremum for all epsilon. Epsilon can be as close as to 0 as you want. So this, you cannot actually feel the difference. Also, Salaudin Marhajiv calculated, for instance, the norm to have an idea what is grand space. Sometimes it's good to look at fundamental function. Fundamental function is a norm of characteristic function of a set. So you probably remember that fundamental function for LP is eta to the power 1 over p. So now you can see how it's difference between the grand space and regular LP. And this result is due to Salaudin, who is here. Actually, it was calculated first, it was approximated by Alberto Fiorenza, by analytic methods, but Solodin calculated with the use of Lambert function explicitly. Okay, so these are some ideas. Now, I said that LP grant is bigger than LP, and for instance, an example that, of a function that belongs to LP grant, for instance, 1 over t to the power 1 over p. This function belongs to LP grant. Of course, this function does belong to regular LP, because 1 over t is not integrable. But you may ask, okay, this works for measurable functions, for real functions. Holomorphic functions, it's a very small set inside of measurable functions. It probably inside of holomorphic functions this doesn't work, so maybe there are no examples. Still, there are examples. For instance, this is an example of a function. We know this function is from Bergman space. Bergman space is an intersection LP with holomorphic functions. So this function belongs to Bergman space if and only if lambda is such. And we proved that this function with lambda equals to 2 over p belongs to Grant space with theta equals to 1. With theta arbitrary, we can have this example. Okay, so even in the case of holomorphic functions, if you even restrict to this very nice space, you still have a difference between Grant space and regular LP space. So our study makes sense. Now, that's what people usually start with, references. I don't list all references for Grant spaces. I just listed a few papers, few first papers. When people speak about Grant spaces, people usually refer to Ivanes Bordone. This guy is, people say that this guy is invented this Grant spaces, the names of Greco, Di Fratta, Fiorenza, Karadjov. Usually you can see in literature these names when you just look at internet for granted small spaces. And of course, there are so many papers after that. So many papers, even books already. But about holomorphic situation, I know only just these 3 papers. This is unpublished yet. I'm speaking about these papers now, So only 3 papers in the holomorphic case, though the holomorphic case presents very nice field for some play, for some experiments with grandization. And since I speak about grandization, of course, when you think about grandization, you call names Samko and Varkhadjiev. Basically, in their works, they started with the idea. Well, you see on the first slide, I didn't mention, but here the situation works only for bounded domain, for bounded measure domain. You see? So this definition on whole theory works only for domain with a bounded measure. Omega equals to 1 does much matter because just to have Euler inequality with constant 1. It can be not necessarily 1, but bounded. Then Samko and Varkhadjiev raised the question, what about Grant space for infinite domain? And they founded a method how to define Grant space in the case of infinite domain. They called this grandization procedure after Solodin defended his thesis, doctoral thesis here at Southern Federal University. Well, but later they even start to think about agrandization for a finite measure domain, referring agrandization to a certain subset of a domain. That means that they don't look at agrandization at every point, only at agrandization of a point of a certain curve, for instance, of a certain sense. Okay? So they call this method of local agrandization because you just take a subset of your domain and you aggrandize with respect to this particular set, not with respect to all points of your domain. And this makes a lot of sense for holomorphic functions, because when you consider holomorphic functions, you know that they are very good inside, of disk, for instance, you don't need to aggrandize the space inside. You have nothing else, the same. But the issue is what's going on when approaching to the boundary. And it makes much sense to aggrandize only at the circle. So this theory works very well, for instance, in the case of allomorphic functions. That's why we started to apply this approach. And first of all, what we did, we generalized the approach for a GL excitation, and they applied the approach for our case of allomorphic functions. Basically, what we proved is the following. This is a very particular result, just for illustration. We proved that this classical norm can be rewritten in this form. So these norms are equivalent. Here we have our aggrandizer, and you can see we get rid of p minus epsilon here. That's very important, because once you think about operators in ground space, you need to think about boundedness or something else with respect to all parameters p minus epsilon. Now you don't move your p. Okay, of course you move weight, but people know how to work with weights. Now, sometimes working with weights easier than working with variable parameter p. Okay, you don't need to care about how norm of operator behaves when you approach to some particular p0. Okay, I'm not saying that this is much easier. In some situations that may be easier. Okay, well, of course we replace this with a general function. We call it aggrandizer, and we prove not only for Lebesgue space but for weighted Lebesgue space and for Morris space. We didn't manage to prove for Orlich because of many technicalities related to the definition of norm. But it may be open equation. It may be an open question. I don't know how much time I have.
You still have about 17 minutes.
17, okay. Well,
could you please get back to one slide? Maybe this is a misprint. You have the power p in the second line, but the power 1 over p minus.
yes, it's a misprint. Of course, it's p. Sorry. Yes, it's a p. Thank you. Just copy paste problem. Sorry. Okay. Just very quick. I will use Orlich-Matyushevska indexes just for statements. In our case, even this definition is easier because we will use quasi-monotone functions, and for quasi-monotone functions, the Orlich-Matyushevska indexes like this. You know, I will also need definition of doubling condition. You know, most of you know this doubling condition and reverse doubling condition. And what else? Well, almost increasing, almost decreasing. So I believe that everyone knows these definitions. Okay, now I come to the general definition of aggradization. So we have a set lambda. Okay, we have a subset F, and we have a normed space X over this lambda, okay, with some distance. To every normed space, we associate X omega. We call it weight, but it is not necessarily weight. In a sense, for instance, when you consider integral norm, they can put weight aside to differential, or you can put aside to a function. But when I call weight, I mean that this space is parameterized by a certain functional parameter. It can be at every place of your norm. It can have very rare interns in your norm. I don't care about it. It may be not a weight in general in our understanding, but for simplicity, I will call this a weight. But basically, this is kind of functional parameters. We have a couple of X and W. Okay, just independent functional parameter. Okay, with the only condition that when W is 1, you must have the same space. Okay, so this is very simple. And delta F is a distance to this set. Okay, so it's a distance calculated from every arbitrary point. Okay, What else? D is diameter, etc. Only one assumption, that if you have weight V greater than U, then you have this inequality for norm for every function. Only one assumption we have, nothing else. So our definition is here. We define a grand space that G is for grand, for aggrandization. F is for this set F, local set. A is for our aggrandizer, and theta is a general parameter. You can see theta here, power of epsilon. So you take the weighted space with this weight. You take composition of aggrandizer with a distance. Aggrandizer has the property that A of 0 is 0 as a limit. So this makes sense, right? L is positive, but actually I don't care about L. So you don't see L here because we don't care about L. And by definition, this our initial space is inside of our bigger space. Okay. Now, let us think about what we got, what we have, what are the properties we have. First of all, I already said that I don't care about L because for different L you have this two-sided estimate that makes that allows us to not to care about. You can take an arbitrary L, so I don't even include in the norm. Another useful property, then you can just take a grand norm only close to the set F. So you take just neighborhood of the set F, you calculate grand norm only here, and the rest you can take just regular norm in your initial space X. It's also sometimes useful. Okay. Now, if you somehow estimate A less or equal than CB to the power alpha, then you have this inclusion. And alpha is an arbitrary. And of course, this is natural. If you have a bigger set, then your space, your aggrandized space is bigger. It's natural. You aggrandize with a bigger set of points. Okay, so you must have bigger space. Well, this is very useful. You see, you can raise your aggrandizer to any power, absolutely any positive power. When you have calculations, you arrive at some construction when your aggrandizer is raised to some power, which is not convenient to your initial norm. You can just forget about this power, just replace with any arbitrary power up to a constant. So this is very powerful statement. And the same to this. Well, in case of course, it's part of this case. If both functions have the positive lower Orlich-Matuszewska indices, then the corresponding spaces coincide, aggrandized spaces coincide up to norm equivalence. Arbitrarily, absolutely arbitrary functions. So this also allows you to just replace one function which doesn't suit you with arbitrary, more visible function for calculations. Well, now these are the main properties of our aggrandized space. Now, maybe the first question should be whether this inclusion is strict, whether this is a real aggrandized space. And we have an example, but we need additional conditions. You see, before that, I didn't impose any condition except one very mild condition. But now I have to impose this, of course, natural condition. First of all, x0 is for the set F. Due to some property I mentioned, we can replace this set F with just one point set x0. If we prove the result for this, then it's sufficient for us, enough for us. So if you have two balls and radius is bigger, then you have this estimate. It's very natural. Okay? To ask. And also the condition on so-called weight. You must have a function, depends on the space X, such that if you have a constant weight, that you must be able to estimate your weighted space with a constant weight with initial space. You remember, X with weight 1 must be 1, but X with weight C must be estimated by up to a constant It's very with a norm of initial space x. It's a quite natural condition and quite mild condition. Okay, so only these two conditions. And we take this function, again, we take characteristic function of a ball. We calculate function f0 as the characteristic function calculated at this distance. And we easily can prove, of course, under assumption that the norm of x is absolutely continuous. So under this also assumption, we can easily prove first this inequality, but this is a contradiction, because if the norm is absolute continuous, this must go to 0 when you squeeze r, and r goes to 0. Instead it's always bigger than 1. So this is a contradiction. This function does not belong to initial space. Now we have to prove that this function belongs to our aggrandized space. And we do this under these conditions. So here we have this defined before functions, nu and function phi from our assumption. Under this condition, our function belongs to aggrandized space. So this is an example. And in case when this fundamental function possesses doubling property, we can even simplify this condition. You can see very nice, very simple condition to have the issue that our function f0 belongs to the aggrandized space. So now we answered the main problem equation, whether we have a real grand or aggrandized space. We do have. Okay. Probably I need to ask how much time?
7.
Okay, so I will be short. Now I come to my second part of my talk, and these are just definitions, nothing else. Definition of LP space, definition of weighted LP space. I will aggrandize these spaces. These definitions for classical grand construction, these are still classical. You take supremum of this norm p minus epsilon in case you take supremum of p minus epsilon norm in weighted space, nothing else. The classical understanding of grand space. And we call AP theta and P theta with rho the corresponding subspaces of holomorphic functions, intersection with holomorphic functions. I'm sorry. And also the definition of Morris space. That's a well-known definition of Morris space. And this is definition of grand Morris space. So you just replace LP with grand LP, nothing else. These are classical definitions. Now I will aggrandize in our scheme. So you can see the norm. This is the weight, the initial weight, and this is our aggrandizer here. And of course you have here p instead of p minus epsilon. So this is our aggrandizing construction applied to the case of weighted Lebesgue space. And first result, if we have, for instance, this condition on weight and aggrandizer, then you have this inclusion. I would say just one word about it. You see, you have here power delta. Delta isn't arbitrary. It means that you can take delta as small as you want. If your aggrandizer have a 0 of like very high power 0, then you can just reduce this power just taking small delta. You see? So this is very powerful. And you can cancel any singularity. Of course, you cannot cancel the exponent singularity, but any power singularity, you can cancel it. So under this condition, we have inclusion of our local space, aggrandized space, into classical space. Vice versa. Two cases, depending on rho is almost decreasing or almost increasing, but in any case, you can see the conditions to have the classical ground space is inside our local aggrandized space. And here also eta power is just arbitrary. You can play with eta. You can take eta as you want, as you wish, just to have this. Um, in case of power weight, we can just reduce the above conditions to these two simple conditions, and we have coincidence after norm equivalence. Now, under these two conditions, we have coincidence of classical space and our aggrandized space. And of course, as a corollary, in case if you take aggrandizer with the Orlich-Matuszewska index positive, then with arbitrary such aggrandizer, we have the equivalent space to the classical one. With arbitrary. So you can take what you want for your particular needs. Now, aggrandization of Morris space. We take norm of Morris space, put here our aggrandizer, and that's it. So nothing else. Okay? And again, we have similar results. Under this condition, we have this inclusion, and under this condition, we have this inclusion. And also, of course, if this condition satisfied, both satisfied, then you have coincidence of spaces up to equivalence of norms. And again, here also parameters beta is quite arbitrary. So you can play this initial function, phi is an initial function that defines the Morris space. So to achieve this inequality, you can take beta and arbitrary. It's in your possession. It's up to you how to take beta. So it's very important that and also delta here. It's very important that our parameters are arbitrary parameters. So you can just adjust situation for your needs, for your situation, for your problem. How much time I still have?
2 minutes.
Okay. Okay, so, well, I will not speak about this. This is kind of application. Probably I will stop here. Maybe 4 questions.